The universe has existed forever. It was born around 13.82 billion years ago. Matter, energy, space, and time erupted into being in a fireball called the Big Bang. It expanded, and from the cooling debris, there congealed galaxies, islands of stars of which our Milky Way is one of about 2 trillion. This is the Big Bang Theory, the supreme theory describing our cosmic origins. But even if the Big Bang Theory is treated as a de facto way the universe began, it's had some issues. Let's face it, to think that the universe has a history that started with a kind of birthday some 13.8 billion years ago is, well, weird. If everything that happens can be attributed to a cause, what caused the universe? And if attributing the beginning of everything to the Big Bang, well, what happened before that? What existed before Big Bang? It's a question that has vexed scientists for a long time.
Before the Big Bang, it's an interesting question because that's...
I'll just repeat, there's no data to base anything on, right? It's an open question at present.
Oh dear, that's a really big question. Well, I try not to think of what happened before Big Bang because I don't think there is an answer for it.
But now, in a world-shattering revelation, physicist and professor of particle physics Brian Cox declared that he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head.
We used to think that the universe emerged in that state, very hot and very dense at the beginning of time. And we used to call that the Big Bang. But now we strongly suspect that the universe existed before that. And in that sense, it's possible to speak of a time before the Big Bang.
Join us today as we dig deep into how Brian Cox debunks Big Bang with the creation story which came before the existence of the universe. Professor Brian Cox has transformed his field of science in the 21st century into something accessible to everyone, regularly contributing to public debate and discussion. Never one to shy away from the big questions, the physicist Brian Cox previously took on the story of the Big Bang. Its early conception was first suggested in the 1920s by the Belgian priest called Georges Lemaitre, who theorized the universe began from a single point, a lone primordial atom. This idea was later developed by others to make a set of additional predictions. Number 1, the universe as we see it today is more evolved than it was in the past. The farther back we look in space, the farther back we're also looking in time. So, the objects we see back then should be younger, less gravitationally clumpy, less massive, with fewer heavy elements, and with less evolved structure. There should even be a point beyond which no stars or galaxies were present. And number 2, at some point the radiation was so hot that neutral atoms couldn't stably form, because radiation would reliably kick any electrons off the nuclei they were attempting to bind to. And so there should be a leftover, now cold and sparse, bath of cosmic radiation from this time. And point number 3, at some extremely early time, it would have been so hot that even atomic nuclei would be blasted apart, implying there was an early, pre-stellar phase where nuclear fusion would have occurred. Big Bang nucleosynthesis. From that, we expect there to have been at least a population of light elements, and their isotopes spread throughout the universe before any stars formed. In conjunction with the expanding universe, these 4 points would become the cornerstone of the Big Bang Theory. The growth and evolution of the large-scale structure of the universe, of individual galaxies, and of stellar populations found within those galaxies, all validates the Big Bang's predictions. The discovery of a bath of radiation just 3 Kelvin above absolute zero, combined with its black body spectrum and temperature imperfections at microkelvin levels of tens to hundreds, was the key evidence that validated the Big Bang and eliminated many of its most popular alternatives. And the discovery and measurement of the light elements and their ratios, including hydrogen, deuterium, helium-3, helium-4, and lithium-7, revealed not only which type of nuclear fusion occurred prior to the formation of stars, but also the total amount of normal matter that exists in the universe. Extrapolating back to as far as your evidence can take you is a tremendous success for science. The physics that took place during the earliest stages of the hot Big Bang imprinted itself onto the universe, enabling us to test our models, theories, and our understandings of the universe from that time. The earliest observable imprint, in fact, is the cosmic neutrino background, whose effects show up in both the cosmic microwave background, the Big Bang's leftover radiation, and the universe's large-scale structure. This neutrino background comes to us, remarkably, from just 1 second or so into the hot Big Bang. All of this makes the Big Bang theory largely acceptable to be the event behind our existence. However, Professor Cox has another idea. He argued there was a time before the Big Bang, a time in which the universe did not exist at all. He explored this in his documentary series, Universe, where everything begins and ends, stating that before the launch point of the Big Bang, there was no matter at all. All that existed was space-time and an ocean of energy, almost still but gently rippling. This place, as he said, should be imagined as a near-still ocean of energy filling the void. It would have had no structures, and the energy in the space would have caused it to stretch violently, something known in space as inflation. Flipping the Bible creation story on its head, Professor Cox proceeded to explain the science creation story. And the crux of the story, he said, is an unimaginably violent expansion, which is known as inflation. He said, quote, "In the beginning, there was an ocean of energy that drove a rapid expansion of space known as inflation. There were ripples in the ocean. As inflation ended, the ocean of energy was converted into matter by the Big Bang. And the pattern of the ripples was imprinted into our universe as regions of slightly different density in the hydrogen and helium gas that formed shortly after the Big Bang. The denser regions of gas collapsed to form the first stars and the first galaxies. And 9 billion years later, a new star formed in the Milky Way, the Sun. The star was joined by 8 planets, including Earth. And nearly 13.8 billion years after it all began, we emerged, blinking into the light, he said.
In the beginning, there was an ocean of energy that drove a rapid expansion of space, known as inflation. There were ripples in the ocean. As inflation ended, the ocean of energy was converted into matter.
When cosmic inflation was first put forth and developed in the early 1980s, it separated the two definitions of the Big Bang, proposing that the early hot, dense state never achieved these singular conditions, but rather that a new, inflationary state preceded it. There really was a universe before the hot Big Bang, and some very strong evidence from the 21st century truly proves that it is so. In a hot Big Bang that we extrapolate all the way back to a singularity, the universe achieves arbitrarily hot temperatures and high energies. Although the universe will have an average density and temperature, there will be imperfections throughout it, overdense regions and underdense regions alike. Also, the universe expands and cools. It also gravitates, meaning that overdense regions will attract more matter and energy into them, growing over time, while underdense regions will preferentially give up their matter and energy into the denser surrounding regions, creating the seeds of an eventual cosmic web of structure. But the details that will emerge in the cosmic web are determined far earlier, as the seeds of the large-scale structure were imprinted in the very early universe. Today's stars, galaxies, clusters of galaxies, and filamentary structures on the largest scales of all can be traced back to density imperfections from when neutral atoms first formed in the universe, as those seeds would grow over hundreds of millions and even billions of years into the rich cosmic structure we see today. Those seeds exist all throughout the universe and remain even today as temperature imperfections in the Big Bang's leftover glow, the cosmic microwave background. As measured by the WMAP satellite in the 2000s and its successor, the Planck satellite, in the 2010s, these temperature fluctuations are observed to appear on all scales, and they correspond to density fluctuations in the early universe. The link is because of gravitation and the fact that with general relativity, the presence and concentration of matter and energy determines the curvature of space. Light has to travel from the region of space where it originates to the observer's eyes, and that means point, the overdense regions, with more matter and energy than average, will appear colder than average, as the light must climb out of a larger gravitational potential well. Point, the underdense regions, with less matter and energy than average, will appear hotter than average, as the light has a shallow than average gravitational potential well to climb out of. And point, and that the average density regions will appear as an average temperature, the mean temperature of the cosmic microwave background. But where did these imperfections come from initially? These temperature imperfections that we observe in the Big Bang's leftover glow come to us from an epoch that's already 380,000 years after the start of the hot Big Bang, meaning they've already experienced 380,000 years of cosmic evolution. The story is quite different, depending on which explanation you turn towards. According to the singular Big Bang explanation, the universe was simply born with an original set of imperfections, and these imperfections grew and evolved according to the rules of gravitational collapse, of particle interactions, and of radiation interacting with matter, including the differences between normal and dark matter. According to the inflationary origin theory, however, where the hot Big Bang only arises in the aftermath of a period of cosmic inflation, these imperfections are seeded by quantum fluctuations, that is, fluctuations that arise due to the inherent energy-time uncertainty relation in quantum physics that occur during the inflationary period, when the universe is expanding exponentially. These quantum fluctuations, generated on the smallest scales, get stretched to larger scales by inflation, while newer, later time fluctuations get stretched atop them, creating a superposition of these fluctuations on all distant scales. These two pictures are conceptually different, but the reason they're interesting to astrophysicists is that each picture leads to potentially observable differences in the types of signatures we'd observe. In the singular Big Bang picture, the types of fluctuations that we'd expect to see would be limited to the speed of light, the distance that a signal, gravitational or otherwise, would have been allowed to propagate if it were moving at the speed of light through the expanding universe that began with a singular event known as the Big Bang. But in a universe that underwent a period of inflation prior to the start of the hot Big Bang, we'd expect there to be density fluctuations on all scales, including on scales larger than the speed of light could have allowed a signal to travel since the start of the hot Big Bang. Because inflation essentially doubles the size of the universe in all three dimensions, with each tiny fraction of a second that passes, fluctuations that occurred a few hundred fractions of a second ago are already stretched to a scale larger than the presently observable universe. Although later fluctuations superimpose themselves atop the older, earlier, larger scale fluctuations, inflation allows us to start the universe off with ultra-large scale fluctuations that shouldn't exist in the universe if it began with a Big Bang singularity without inflation. In other words, the biggest test that one can perform is to examine the universe in all its gory details and look for either the presence or absence of this key feature, what cosmologists call superhorizon fluctuations. At any moment in the universe's history, there's a limit to how far a signal that's been traveling at the speed of light since the start of the hot Big Bang could have traveled, and that scale sets what's known as the cosmic horizon. Scales that are smaller than the horizon, known as subhorizon scales, can be influenced by physics that occurred since the start of the Big Bang. Scales that are equal to the horizon, known as horizon scales, are the upper limit to what could have been influenced by physical signals since the start of the hot Big Bang. And scales that are greater than the horizon, known as superhorizon scales, are beyond the limit of what could have been caused by physical signals generated or since the start of the Big Bang. In other words, if we can search the universe for signals that appear on superhorizon scales, that's a great way to discriminate between non-inflationary universe that began with a singular hot Big Bang, which should have had them all, and an inflationary universe that possessed an inflationary period prior to the start of the hot Big Bang, which should possess these superhorizon fluctuations. Unfortunately, simply looking at a map of temperature fluctuations in the cosmic microwave background isn't enough, on its own, to tell these two scenarios apart. The temperature map of the cosmic microwave background can be broken up into different components, some of which occupy larger angular scales on the sky, and some of which occupy small angular scales, as well as everything in between. The problem is that fluctuations on the largest scale have two possible causes. They could be created from the fluctuations that arose during an inflationary period, sure, but they could also be created simply by the gravitational growth of structure in the late-time universe, which has a much larger cosmic horizon than the early-time universe. For example, if all you have is a gravitational potential well from a photon to climb out of, then climbing out of that well costs the photon energy, that is known as the Sachs-Wolf effect in physics, and occurs for the cosmic microwave background at the point at which the photons were first emitted. However, if your photon falls into a gravitationally potential well along the way, it gains energy, and then when it climbs back out again on its way to you, it loses energy. If the gravitational imperfection either grows or shrinks over time, which it does in multiple ways in a gravitating universe filled with dark energy, then various regions of space can appear hotter or colder than average based on the growth or shrinkage of density imperfections within it. This is known as the integrated Sachs-Wolf effect. So, when we look at the temperature imperfections in the cosmic microwave background, and we see them on these large cosmic scales, there isn't enough information there on its own to know whether 1. They were generated by the Sachs-Wolf effect and are due to inflation, or 2. They were generated by the integrated Sachs-Wolf effect and are due to the growth or shrinkage of foreground structures, or 3. Or they're due to some combination of the preceding two. Fortunately, however, looking at the temperature of the cosmic microwave background isn't the only way we get information about the universe. We can also look at the polarization data of the light from that background. As light travels through the universe, it interacts with the matter within it, and with electrons in particular. Remember, light is an electromagnetic wave. If the light is polarized in a radially symmetrical fashion, that's an example of an E-mode or electric polarization. If the light is polarized in either a clockwise or counterclockwise fashion, that's an example of a B-mode or magnetic polarization. Detecting polarization on its own isn't enough to show the existence of superhorizon fluctuations, however. What you need to do is perform a correlation analysis between the polarized light and the temperature fluctuations in the cosmic microwave background, and correlate them on the same angular scales as one another. This is where things get really interesting, because this is where observationally looking at our universe allows us to tell the singular Big Bang without inflation, and the inflationary state that gives rise to the hot Big Bang scenarios apart. Bottom of form. In both cases, we expect to see sub-horizon correlations, both positive and negative ones, between the E-mode polarization in the cosmic microwave background and the temperature fluctuations within the cosmic microwave background. In both cases, we expect that on the scale of the cosmic horizon, corresponding to angular scales of about 1 degree and a multipole moment of about 1 equals 200 to 220, these correlations will be zero. However, on superhorizon scales, the singular Big Bang scenario will only possess one large, big blip of correlation between the E-mode polarization and the temperature fluctuations in the cosmic microwave background, corresponding to when stars form in large numbers and reionize the intergalactic medium. The inflationary Big Bang scenario, on the other hand, includes this, but also includes a series of negative correlations between the E-mode polarization and the temperature fluctuations on superhorizon scales, or scales between about 1 and 5 degrees, or multipole moments from 1 equals 30 to 1 equals 200. What you see above is the very first graph published by the WMAP team in 2003, a full 20 years ago, showing what cosmologists call the TE cross-correlation spectrum, the correlations on all angular scales that we see between the E-mode polarization and the temperature fluctuations in the cosmic microwave background. In green, I've added the scale of the cosmic horizon, along with arrows that indicate both subhorizon and superhorizon scales. As you can see, on subhorizon scales, the positive and negative correlations are both there. But on superhorizon scales, there's clearly that big dip that appears in the data, agreeing with the inflationary or solid line prediction, and definitely not agreeing with the non-inflationary singular Big Bang dotted line prediction. Of course, that was 20 years ago when WMAP satellite was superseded by the Planck satellite, which was superior in many ways. It viewed the universe in a greater number of wavelength bands, it went down to smaller angular scales, it possessed a greater temperature sensitivity, it included a dedicated polarimetry instrument, and it sampled the entire sky more times, further reducing the errors and uncertainties. When we look at the final 2018 era Planck TE cross-correlation data below, the results are breathtaking. As you can clearly see, there can be no doubt that there truly are supersized horizon fluctuations within the universe, as the significance of this signal is overwhelming. The fact that we see superhorizon fluctuations, and that we see them not merely from reionization, but as they are predicted to exist from inflation, is a slam dunk. The non-inflationary singular Big Bang model does not match up with the universe we observe. Instead, we learn that we can only extrapolate the universe back to a certain cutoff point in the context of the hot Big Bang, and that prior to that, an inflationary state must have preceded the hot Big Bang. We'd love to say more about the universe than that, but unfortunately, those are the observable limits. Fluctuations and imprints on larger scales leave no effect on the universe that we can see. There are other tests of inflation that we can look for as well, a nearly scale invariant spectrum of purely adiabatic fluctuations, a cutoff in the maximum temperature of the hot Big Bang, a slight departure from perfect flatness to the cosmological curvature, and a primordial gravitational wave spectrum among them. However, the superhorizon fluctuation test is an easy one to perform, and one that's completely robust. All on its own, it's enough to tell us that the universe didn't start with a hot Big Bang, but rather that an inflationary state preceded it and set it up. Although it's generally not talked about in such terms, this discovery, all by itself, is easily a Nobel-worthy achievement. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. As always, thanks for watching, and we'll see you next time.